Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be covering the quantum mechanics associated with the model of an atom and light and its fundamental properties. Let's get started. So as I mentioned, this video is kicking off chapter 7, which is focusing on understanding the quantum mechanical model of the atom. We're going to learn a little bit about light and its behavior and different properties associated with it before we jump into the overall quantum mechanics associated with an atom. So we want you to remember that the atom is extremely small. And because we're trying to examine the behavior of these really, really small things, it could actually make it even harder to understand these very small subatomic particles and how they impact things that are found within the atom. So I just want to remind you guys, we learned about electrons back in chapter 1, and we know that it's one of the subatomic particles that's located within the atom. And we saw then that the weight, the mass of an electron is at 10 to the negative 28. So, I mean, it's so tiny that in fact, a single speck of dust would have more electrons on it than the number of people that live in Earth. So that's how small of a particle that we're dealing with. However, these really small things, they contribute to the bulk of the behavior that we see in many of the atoms. And they're so small that even trying to directly observe the electrons in an atom is near impossible. So it makes it very difficult to understand the power that these small subatomic molecules or these small subatomic particles have. Now, the theory that explains the behavior of the atom is what we know as the quantum mechanical model, and this explains how and where electrons exist and behave within an atom. It's also going to help us to understand and predict certain properties that will be associated with different atoms and determine how they are related to one another. So some of the things that we're going to know after this completion of this chapter is understand why certain elements are considered metals versus others are non-metals, why some elements have more likelihood of gaining electrons versus others that tend to lose electrons and form anions. We're going to learn what makes certain atoms be very reactive while others are inert. And we're going to see that many of these patterns do exist in this periodic nature that is inherent to how the periodic table is laid out. So the main way that we study the electrons and their behavior is through their interaction with light. So I'm going to spend some time actually defining what light is and ground setting some things so that we understand the behavior and the functionality of light. So light is considered to be a form of electromagnetic radiation. And the light waves, they consist of perpendicular oscillating waves, which I'll show you for you in a second, that consist of an electric field and a magnetic field. And so light is moving very, very fast. If you've ever watched Superman, it says faster than the speed of light. So the speed of light is at 3.0 times 10 to the 8th meters per second. So that's 3.0 times 10 to the 8th meter in 1 second. That's how fast light is traveling. And all electromagnetic waves move at this pace in space at this constant speed. So the constant that we reference is the constant c. And again, that represents our speed of light at 3.0 times 10 to the 8th meters per second. Now, as I mentioned in the previous slide, light consists of those two perpendicular oscillating waves, the electric field and the magnetic component. But you can see that light does travel in that unified straight line direction when it is in motion. Now, if we look at the wave itself, there's some terminology that we'll want to be familiar with that's going to be essential in the calculations that we're going to be doing. And so the wave itself, whether it is a big wave like what is shown on the screen, or if it's a really, really tiny wave, there's some parameters that we like to be able to identify within the wave itself. So the first parameter is what we call the wavelength. And so the wavelength is the distance between the two peaks of a wave. And so that wavelength can be extremely large, like what you see shown in the slide, or it could be smaller, like what I've drawn here. Now, the symbol for wavelength is the Greek symbol lambda, and it looks like kind of like a sideways T. And so different types of waves, different types of electromagnetic radiation have different wavelengths. Some have very long wavelengths, some have very short wavelengths. But remember, regardless of the type of light it is, that all light is moving at that same speed, that speed of light of 3.0 times 10 to the 8th meters per second. Now, we also have another property associated with light that we want to know, and that's what's called the frequency. Okay, so the frequency, which is Greek symbol nu, it looks kind of like a sideways V or a cursive V. Nu, the frequency is based on how often the waves would hit a certain point as it is traveling at that speed of light. So imagine if we had a wall here. Those waves, depending on if they're large waves or short waves, are going to have a different frequency in regards to the number of waves that would strike that surface at that time, or that pinpoint, that standpoint at that time. So let's think about it. If we have long wavelengths versus short wavelengths, which one would you expect to hit this point more frequently? And so we would think that something with the shorter wavelengths, well, those waves are going to just keep crashing into that point over and over again. As the bigger wave, the ones with the longer wavelengths, it's going to take more time for them to go and hit that point. And so the take-home message you should get from that is that there's an inverse relationship between the wavelength of a magnetic form of magnetic radiation and the frequency. The longer the wavelength, the shorter the frequency, or vice versa, the shorter the wavelength, the higher the frequency. And then the amplitude, which is again how tall, how high are those waves, those peaks, will also determine other properties such as like the brightness of a color that we may observe. Now, when we're characterizing waves, as I mentioned, we'll want to be able to define that frequency. And the frequency is the number of waves that pass a point in a given period of time. And so again, if we saw those really large wavelengths, we would expect to have shorter frequency, a shorter number of waves that would pass that point within a given number of time. Or if we were dealing with a a shorter wavelength, then we would expect a higher frequency. Now, the units, I didn't mention the units on the previous slide, but the units for wavelength are meters, so it's a length unit. And then the unit for frequency is inverse seconds, or seconds to the -1, or what we like to call hertz. And so you may see Hz represented in these problems. So Hg just simply represents hertz. Now, another component of these waves that we can tie into here, along with the speed of light, the frequency, and the wavelength, is the amount of energy associated with a particular form of this radiation or light energy. And the total energy is directly proportional to the amplitude of the waves, how tall they are, as well as the wavelength. So when we look at the amplitude, the more force that particular wave is going to have, and the more frequently that the wave strikes, the more force there will be. So again, as we look at the short wavelengths versus longer wavelengths, that shorter wavelength, which would ultimately have a higher frequency, would also yield a higher energy when it comes to correlating all these different parameters. Okay. And so remember, the waves are traveling at the same speed, that speed of light, and that again, shorter wavelengths will have a higher frequency. We can combine those variables together through a very simple calculation or an equation, which is shown for you on the slide. And so what this means is the wavelength and the frequency of electromagnetic waves are inversely proportional, not directly inversely. They are inversely proportional, and they're tied together through this speed of light constant. And so we can see here that the frequency is equal to the speed of light divided by the wavelength. Okay, and remember, speed of light is units of meters per second. That's that constant, 3.0 times 10 to the 8th meters per second. The wavelength would be based on that distance between the peaks or the waves, and then the frequency that would be how often peaks are hitting a certain point. And so if you'd like that triangle learning tool that I showed you in previous videos for density and molarity, guess what? You can use it here as well. So you can say that the frequency is equal to the speed of light divided by the wavelength. And remember how this works is that you simply cover up the one that you're solving for. And remember that this horizontal line means that you divide by that variable. This perpendicular line to that means you multiply by that variable. So you cover up the one you're solving for, and then you'll see the equation for the corresponding variable. Okay? So let's put that to action. So here it says we want to calculate the wavelength in nanometers of red light with a frequency of 4.62 times 10 to the 14 inverse seconds. And so with this type of problem, you'll want to ask yourself, well, what do I know? Because again, there's a lot of different variables here, so you want to make sure you're staying on top of those. So we're looking to calculate the wavelength in nanometers. And what we know is that we have the frequency. The frequency is 4.62 times 10 to the 14 inverse seconds, or we could say hertz. Well, now, if we know our original equation for the light equation is that frequency is equal to the speed of light divided by the wavelength. So therefore, the wavelength would equal our speed of light divided by our frequency. Again, triangle if you need it. Cover up the one we want to solve for. So that means that it is the speed of light divided by the frequency. And then we plug in. So we would say 3.0 times 10 to the 8th. Remember, that is a constant that you would be able to plug in. It may not be stated in the problem for you. And then divided by our frequency, which is 4.62 times 10 to the 14. Now, when we plug this in, we see that we have 3 e to the 8th divided by 4.62 e to the 14th. And what we end up getting is 6.49 times 10 to the 1, 2, 3, 4, 5, 6, 7, 10 to the 7th. And the units here would be, well, seconds and seconds cancel. So this would be meters. But now notice it does ask us to solve for the problem in nanometers. So we would want to do a quick calculation to convert. So if you don't remember your conversions, go back to our chapter 1 videos where I talked about your conversion. So we would do 6.49 times 10 to the 7th meters. And we're going to convert to nanometers real quick. So we know we put meters on the bottom, nanometers on the top. 1 nanometer is 10 to the negative 9 meters. And so we multiply that number by 1e to the negative 9. And we end up getting 6.49 times 10. And sorry, this is to the negative 7 here. Negative 7 here as well. 6.49 times 10 to the 2 would be your final answer. So let's move on to the next problem. The next problem says calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. So again, we're looking for the wavelength, and we just saw that that formula is equal to the speed of light divided by the frequency. And what we know is the frequency is 100.7 megahertz. Remember, we also already know C as well. We know that speed of light constant, so we really should be in a position to be able to plug into our equation. But what you should notice is our units. Our units for frequency are not necessarily in the ideal units that we would need them to be in order for us to be able to cancel out when we're using our speed of light. Right now we're in megahertz. We would prefer to be in hertz or inverse seconds so that we can do that direct cancellation. So our first step would be to convert from our megahertz to just hertz. And so we know that 1 megahertz is 10 to the positive 6 hertz. And then we remember that, well, 1 hertz is actually the same thing as 1 inverse second. And so when we plug that in, we end up with 100.7 times 1e to the 6. And what we end up with is 1.007 times 10 to the 8th inverse seconds for our frequency. And so then we would plug in our wavelength would equal the speed of light value divided by that hertz, that frequency value. And when we solve, we get we end up with 2.98 meters. I hope this video helped you understand light and some of the fundamental properties associated with it. Make sure you guys like, comment, and subscribe, and let me know what other content you would like to see. Be sure to come back for more videos in this series to see more about light and to understand the quantum mechanics associated with atoms. See you guys later. Bye-bye.